So this portion of the lecture, it's going to deal with electrical force. So this is the force. When we talk about opposite attracts and like repel, they attract and repel because of a force. And that force is what we call the electric force or electrical force. So when you have opposite charges, they attract each other. They attract each other with a force. Okay? You can't see the force. That is why we call it a non-contact force or force at a distance, because you can't see the attraction or repulsion. When when you charge a rod negative and you put it towards another negative charge, it repels. Or when you have your negative charge rod and you put it over a piece of paper and it attracts the paper upward, it is a force. Okay, it's a force that pulls that paper uh, that towards the charged object. So that is a non-contact force. There is no contact between the objects we're talking about. Okay, so that force is electrical force. Again, opposite attract and like repel. The strength the strength of the attraction or repulsion depends on the amount of charge that's on the object and the separation distance. Okay, again, the amount of or the strength of the attraction or repulsion, that is the force. It depends on how much charge the object has and the separation distance between the objects. So you can run a little experiment and show that by increasing the charge on the object, you increase the force of either attraction or repulsion, and by uh, decreasing the distance of separation between the objects, you can also increase the force. And this leads us to what the so-called Coulomb's law equation. So the force, the electrical force between two charged objects is equal to K times the charge on one object times the charge on the second object divided by the square of the distance, the separation distance of the objects. Now, it's very important that you know the units that these things are measured in. The SI unit, uh, of course, you know that force is measured in newtons, distance is in meters, and charge is in coulombs. So if you're going to use this equation, you have to make sure your units are your SI units, all right? So again, separation distance between the charges is in meters, force is in newtons, distance is in meters, uh, and charge is in coulombs. So if you rearrange the equation, you can see that the constant and so this Coulomb Coulomb law equation constant is equal to a force times a distance squared divided by charge squared. So that is the unit of the constant. Newton meter squared divided by uh, Coulomb square. That's the charge. Okay, it's important to know that the units have to be the same. So Coulomb's law equation states that the force between two charged objects is directly proportional to the product of the quantity of the charge on the objects. Okay, so you're going to take the charge on one object, the charge on the other object, and you're going to multiply them. Okay, it is inversely proportional to the square of the separation distance between the two objects, or between the objects. So the distance between the objects squared, it is inversely proportional. So if you were to write the equation again, all right, so before we get to that, so if you have like charges, they're gonna repel each other, and the repulsion is the force that we're talking about. So the force of repulsion between these two objects is dependent on the amount of charge that the two objects have. You're going to multiply the charges. The charges have to be in coulombs. So make sure the units are, make sure you use the correct units. So this is repulsion. Attraction, so you have a positive and a negative. The attractive force between these two objects is dependent on the product of the charges. So the charge on one multiplied by the charge on the other. Then you multiply by the Coulomb law constant, and then you divide it by the separation distance squared. You square the distance. So the electrical force is either a push, so it would be a push if they're like charges, and it's a pull if they're opposite charges upon an object as a result of an interaction between electrical charges. Again, the electrical force is a non-contact force, and remember that force is a vector quantity. So when you approaching this type of force, you have to use your addition and subtraction of vectors. So again, the force, and you will get this in your exam, it's going to be very simple, but you have to remember the equation that the force, either a pull or a push, attraction or repulsion, is equal to the Coulomb law constant times the charge on one object, charge on the other object, divided by the separation distance squared. Remember to square the distance. Okay? Coulomb law constant is 9 times 10 to the power 9 Newton meter squared divided by the Coulomb squared. The forces in newtons. Remember the units. Units are very important, and you have to convert when you get a question. Make sure that units correspond. Again, if you have a scenario like this, opposite is gonna, or so use this one. So opposite attracts. So Q1 is going to be attracted to Q2 because they're opposite. The force that pulling them together, that force is equal to K, which is a Coulomb law constant. And it's easy to remember. K is 9 times 10 to the power 9. And then the charge on one times the charge of the other. And then you're going to divide it by the separation distance, the distance between the two charges squared. Square the distance, okay? Remember that. If the charges are the same, then that repulsive force is the same way you calculate it. The repulsive force, K, the amount of charge in one times the amount of charge in the other, divided by the separation distance squared. And when we talk about the distance, it is not the distance from the surface, it is the distance from the center distance, okay? All right. So again, the Coulomb law constant depends on the medium that the charged objects are immersed in. If the charged objects are immersed in here, then that is how we get, because most of our work is in here, so that is why you get 9 times 10 to the power 9 newtons times meter divided by Coulomb squared. If they want to be disgusting in the exam, they could give you a fluid, and then they would give you the constant for that fluid. But the calculation is the same. Okay, so let's do some. The best way to appreciate these questions is to do questions. All right. So question one. Um, all right, so question one states that. Let's. All right. So question one says a positive charge. Sorry, a positively charged object with a charge of plus 85 nanocoulomb. So, okay, so when we talk about charge, because a coulomb is such a large number, remember, a coulomb is a huge number. So that is why we use either microcoulombs or nanocoulombs. And remember, if we say it's a microcoulomb, then it's 10 to the minus 6. If it's nanocoulomb, then it's 10 to the minus 9. So get accustomed to appreciate that. So a positively charged object, a positively charged object with a charge of plus 85 nanocoulomb is being used to balance the downward force of gravity of a 1.8 gram balloon that has a charge of minus 63 nanocoulomb. So the question asks, how high above the balloon must the object be held in order to balance the balloon? So this is a typical question that you'll get in your exam. So what you do, you sit down and you try to understand what they're asking. So you, you have to draw these things. So when you approach these questions, you draw it and then you use a free body diagram just outlining the forces. Okay, so we have a positive charge object, a positive charge object with a charge of plus 85 is being used to balance the downward force of gravity in a balloon. So let's draw it first. So we're just going to draw the scenario. So we have, this is a positive charge object. So just put it like this. So it could be anything. So this object is positive. All right, so it has a positive charge. Okay, and the positive charge is 85 nanocoulombs. But let's wait. It is being used to balance the downward force of gravity on a one with a balloon. So the balloon has a negative charge. So let's just erase this. So if you understand what they're saying, okay. So you have a positive charge object right here. Below that positive charge, you have a negative balloon, negatively charged balloon. Okay, now the this is a positive charge, this is a negative charge. The force between them is attractive. So there's going to be an electrical force pulling this negative balloon upwards. So let's draw this. So the force, this electrical force, this object is pulling the balloon towards it. Okay, and let's call that electrical force. Just say this electrical force right there. But also the balloon has a weight, which is pulling the balloon downwards. Okay, so pulling the balloon upwards is the electrical force. So let's call this force electric. Okay, and then pulling the balloon downward, this is the force of gravity. Force of gravity. Okay, So you always read the question again to make sure you have your scenario correct. A positive charge object with a charge of plus 85 nanocoulomb is being used to balance the downward force of gravity on a 1.8 gram balloon that has a charge of minus 63 nanocoulombs. How high above the balloon the object must be held in order to balance the balloon? So how far above this balloon you're going to hold this positive charge so that the balloon is in equilibrium. So when you say equilibrium, that means it's not moving up and it's not moving downward. So for that to occur, then the electrical force have to balance the downward force of gravity. For the balloon to be stationary, for the balloon to be in equilibrium, the upward electrical force have to be equal to the downward force of gravity. We know that the force of the downward force of gravity, because we did mechanics, so we know that the force of gravity is equal to the mass times acceleration, right? Mass times acceleration, and that's the acceleration of gravity. All right, this is a G, don't worry about it. Okay, so the force of gravity is equal to the mass times the acceleration due to gravity. The mass of the balloon, now they gave you the mass in grams. Okay, we know that our mass should be in kilograms. Okay, the SI units, when you're doing force, your mass have to be in kilograms. So to convert your 1.8 grams into kilograms, you have to divide it by 10. You have to divide it by 10 to the power 3, right? So our mass would be 1.8 times 10 to the power minus 3 to convert the mass to kilograms. You have to make sure if your units are not correct, your calculation is going to be off. So 10 to the minus 3 times G, and G is 9.8 meters per second squared. Okay, so let's do the calculation there. Let's do our calculation. So I tell you what, 1.8 times 9.3 is all right. So let's use our calculator to get that. All right, so we use your calculator. And you can use calculator in the exam. So it's 1.8 times 9.8, and that is equal to 17. That is equal to 17.6. 17.6 times 10 to the minus 3. Right? So this force is in newtons because we use the correct unit. So this is the force due to gravity, and it is balanced by the electrical force. So the electrical force is equal to that force. They want us to calculate distance. That's what they want us to calculate. We know that the electrical force, the force electric, is equal to K. Always write your equation out. Times Q1 times Q2. So in the exam, always write out your equation divided by distance squared. So this distance is so this distance squared here is this distance from the balloon to the charge uh, object right up here, the positive charge object. That's the distance. So this is what we need to calculate. But we know that this is equal to, from right up here, that force of that electrical force is equal to the force due to gravity, which is 17.6 times 10 to the minus 3 times 10 to the minus 3. So we know the charge, okay? We know the charge. The charge in the positive object is plus 85 nanocoulomb. And we know the charge in the balloon. Charge in the balloon is 63 nanocoulomb negative. All right, so let's put these in our equation now. So the coulomb, the you know, so when you're doing questions like this, try to be smart. Try to be smart, and you have to organize your questions. So just looking at this, we want D. The only unknown is D. So if you just take this equation right here, you'll see that D squared, you just rearrange your equation, D squared, right? Just if you rearrange your equation, D squared is equal to K, Coulomb law constant, times the charge on one of the object, Q1, times the charge on the other object, which is Q2, divided by 17.6 times 10 to the minus 3. So a question like this requires you to use some common sense, because if you can do it so that it's very cumbersome, but you don't want to do it so it's cumbersome. So just rearranging this equation, because this electric force is equal to this gravitational force. We want D, the distance from the balloon to the charged object. So D squared is equal to K times Q1 times Q2 divided by 17.6 divided by 3. So when we simplify this, K is 9 times 10 to the power 9. Okay, the charge on this, so the, or 85. So I would not put in the sign, the positive charge and negative charge. You just need to know that positive and negative will attract, and then like charge is going to repel. Do not put your signs in. All right. So the charge on the charge, the positive charge object is 85 nanocoulomb. And as we said, nanocoulomb is 10 to the minus 9. So it's 85 times 10 to the minus 9. And then you're going to multiply it by the charge on the other object, which is, it is negative. You don't have to put the negative in. You know that negative and positive is going to attract. So that's 63 times, it's nanocoulomb, times 10 to the minus 9. Okay, so this just becomes a simple mathematical equation. Okay, we know that when you multiply powers, you actually had the powers. So this one will cancel that. So you're left with 10 to the minus 9. So this is 9. Of course, you have to divide by your, so this would be 9 times 85 times 63. And you're still going to divide by your 17.6 17.6 times 10 to the minus 3. All right, so it's just, as I said, this is just a simple mathematical thing now. So, all right, so let's simplify this. So we have 9 times 85 times 63. So let's simplify that. So it is 9 times 85 times 63. So this gonna give you, all right, so this gonna, so on top, so on top you're gonna have, 48 it is 48,195. So we can simplify that, because this is, all they want you to do is simplify. They don't want you to. So it is 40. All right, let me just write it out and then simplify. 48,195. Okay. And that is, so this 10 to the minus 9 is going to cancel this 10 to the positive 9. So this is times 10 to the minus 9. Okay. All right. And then we have this down below. All right. Did I make a mistake? So this is a 9. This is 85 and that's 63. So okay. So this is 17.6 48.6 times 10 to the minus 3. Okay. All right. So what we can do is we can divide this by this number. Okay. This 48,000. We can divide it. Let's say so. Let's do that. So we can or I tell you what. As again, you're gonna use common sense in doing these problems. So this 48,195 is actually 48.195 times 10 to the power 3. So let's put it like that. 48. All you're doing is simplifying these things. 48.195 times 10 to the power 3. It's the same thing. If you remove this and you just have to put your point 3 space to the right, so it will be 1, 2, 3. So this 48.195 times 10 to the power 3 is the same thing as that. And then you have there times 10 to the power 9. And you're going to divide by. So you always try to simplify your equation. 17.6 times 10 to the power minus 3. All right, so, and that is equal to, so what we can do now, we can divide our 48.195 by, divided by 17.6, and let's see. So that would be 48.195 divided by 17.6, and that's equal to 2.74. So we divide this number by this, so that gives us 2.74. Now, when you're dividing by a negative, a number raised to a negative power, if you take it on top, it's going to become positive. So this will become positive 10 to the power 3. So you have 10 to the power 3 times 10 to the power 3. So you already had a 10 to the power 3 there. And then the one that you're going to divide it by, when you bring it to the top, it becomes positive. And then you have your 10 to the minus 9. Your 10 to the minus 9. Okay, so when you simplify that, so again, when you multiplying powers, you have the power, so this would be 10 to the positive 6, and then you multiply it by 10 to the minus 9, is 10 to the minus 3. So this is 2.74 times 10 to the minus 3. 10 to the minus 3. 10 to the minus 3. So this is distance squared. Okay, that is distance squared. So, all right. So our distance, and again, so your distance is in meters. So this is actually in meters squared. So what you can do to simplify all of that, again, it's just math. So you have to try and simplify things. So you want to get so in order to get distance, you're going to have to get the square root. So what I would do, I would convert this into 27.4 multiplied by 10 to the minus 1. And when you get 10 to the minus 4. So you just convert your two, so this will be 27.4. So if you call this 27.4, you have to multiply by 10 to the minus 1. They are the same thing. And then you have a 10 to the minus 3. So this is equal to, it's just the same thing, you're just writing it another way. 27.4 times 10 to the minus 4. Okay, so when you, so that's d squared. So this is d squared. So to get d now, if you put d right up here, so d is equal to the square root of this. The square root of this. The square root of 27.4 is 5.2. And the square root of 10 to the minus 4 is 10 to the minus 2. Okay, so now remember that this is your distances in meters. So when we say 10 to the minus 2, you have to move your decimal point 2 places to the left. So you're gonna move it 1, 2. So this is actually 0.052 meters. Or you can convert to centimeters, but meters. Okay? Okay? So the balloon, this object, this charge, positive charge object, have to be held 0.052 meters above the balloon for the balloon to remain stationary in equilibrium. But the concept is that the electrical force is going to balance the force due to gravity. So you have to know what your electrical force is. And this distance, again, the electrical force is going to be the distance, the separation distance. That's what we have right here. The separation distance squared. The distance between your positively charged object and your negatively charged balloon. The distance. So your electrical force pulling the balloon downward is going to be balanced by the electrical force pulling the balloon upwards to this charged object. Okay, so that is the concept that you need to grasp. And all right, so let's So I hope you fully understand this. Let's move to question 2. But the concept is the same for all of these questions. You have to draw the rough diagram, then you have to draw the free body diagram. All right, so question 2, a balloon A and a balloon B are charged in a like manner by rubbing animal fur. Each acquires an excess of 25 trillion electrons. So you're going to charge a balloon by rubbing it with animal fur. So you're going to give the balloon a negative charge. So, sorry. So balloon A and balloon B are charged in a like manner by rubbing with animal fur. Each acquires an excess of 25 trillion electrons. So the amount of electrons, so they're going to be charged negative. If the mass of the balloon is 1 gram, then O for balloon B must be balloon A in order to levitate balloon B, assuming the balloons act as a point charge. Okay? So again, so you have to draw the diagram. So you have two balloons, balloon A and a balloon B. All right, so let's draw them. So we have balloon A and we have balloon B. You charge them by friction, by rubbing with animal fur, and all they did was give it the amount of electrons that's on the balloon. So you know that they are negative. So R4 below B must below balloon A to levitate. So when you levitate something, it's held up. So let's say, call this balloon A, okay, and it's charged negative, right? All right, sure. The mass of the balloon, then R4 below balloon B must be A. So let me just erase this. All right. So, all right. So again, they didn't give you the charge. Um, they give you the amount of electrons. So, all right. All right. So again, so like charges is going to repel and opposite charges attract. Okay. So, all right. Balloon A and balloon B are charged in like manner by rubbing. Each acquires an excess. If balloon do that, then all four balloon B must be balloon E. All right. All right. So let's draw it right up here. All right. So let's do this. All right. So this is balloon A. It's negative. So both balloons are negative charge. So you have to put balloon B above A. It also has a negative charge. So the so this balloon, you're gonna someone is gonna hold this balloon right here. It has a negative charge. So what it's gonna do is gonna push away balloon B. So balloon B is gonna be pushed upwards. But so the electrical force is gonna push upwards on balloon B. But balloon B has a weight, and because it has a weight, it's gonna have a force due to gravity, which is pulling it downwards, right? So so you have to read the question and make sure you draw the scenario correctly, because if you don't, you're gonna get it wrong. So balloon A and B, they are charged in a like manner by rubbing with animal fur. So by rubbing with animal fur, they acquire an excess of 25 trillion electrons. So they're both gonna be negative. If the mass of the balloon, they both have the same mass, 1 gram. Then how far below balloon B must be balloon A BL in order to levitate the balloon B. So you're going to hold balloon A down below, balloon B is going to be up top, and balloon A is going to push up on balloon B. But balloon B has a weight, so it has a force due to gravity, which is going to pull it downward. So at a certain distance below B, the forces will be balanced. That is, the electrical force pushing upwards and the force pulling the balloon downward. At a certain distance, they will be equal. So the balloon B will levitate. It will be immersed in air and not moving. Okay? So this is a scenario, and they want you to calculate the distance. That's what they want you to do, calculate the distance. Okay, so all right. So the approach again is the same approach. So force due to gravity pulling balloon B downward is equal to the electrical force pushing upward on balloon B. What is the force due to gravity? All right, so let's do that. So the force due to gravity is equal to the mass times acceleration. Again, the mass, you have to be careful of the unit. It is in grams, so you have to put it in kilograms. So that is 1 times 10 to the minus 3 kilograms. Okay? And then the acceleration due to gravity is 9.8 meters per second squared. So this is the force due to gravity. And because you're using so many 10 to the this and 10 to the that, don't work it out. Don't simplify it yet. Okay? Because a lot of these 10 to whatever power are going to cancel out. So don't simplify it. So the force due to gravity is 1 times 10 to the minus 3 times 9.8. The mass times the acceleration due to gravity. We converted the 1 gram into kilogram. Okay? And that is going to equal to the electrical force. And the electrical force is equal to the Coulomb law constant times the charge on one of the object times the charge on the other object divided by the separation distance squared. Okay? All right. Now, when you look in the equation, they didn't give you a charge. They didn't give you a charge. But if you remember from the earlier lecture, each electron has a charge of 1.6 times 10 to the minus 19 coulombs. So we know the charge then, and each of them have the same charge, right? Each balloon have the same charge, right? Each of the balloon have the same charge. So so you so so you have to be familiar with uh, with numbers a little bit. So this is just so it's now converted. So strictly a little arithmetic. All right. So 25 trillion electrons. What is the charge on 25 trillion electrons? We said an electron. Let's put it right here. Each electron, each electron has a charge of 1.6 times 10 to the minus 19 coulombs. Remember, a coulomb is a huge number. All right, so each electron has this amount of charge. You have 25 trillion electrons on the balloon. So the charge in the balloon is called the charge in the balloon Q. All right, and each balloon is charged to the same amount. So Q, or it doesn't matter. It's a Q1. So the charge in the balloon is 25 trillion. So a trillion is 10 to the power 12. So 20, this is the charge, okay, 10 to the power 12. This is, a trillion is 10 to the power 12. So on each single electron, this is the charge. So you have to multiply the total number of electrons by the charge in each electron to get the total charge. Okay, so you, again, as I said, you don't want to. All right, so let's simplify this. So the charge is 25 times 10 to the power minus 7. So this is the charge. So each of the balloon is charged with 25 times 10 to the minus 7 coulomb. This is coulombs. This is coulombs, okay? So once we substitute this charge in the equation, then the only unknown is distance. All right? So, and again, it's just a simple thing as managing your equation. All right, let's just do it again. Okay? So the force of the electrical force, which is equal to our gravitational force, is equal to K. So we know that K is 9 times 10 to the power 9 times our charge, and the charge is 25. So each of the balloon have the same charge. So 25 times 10 to the minus 7 times 25 times 10 to the minus 7. Okay, and that's divide. You're going to divide that by the distance squared, separation distance between the two balloons. Distance squared. So when you simplify this, so when you get something like this, you multiply the whole numbers, or you multiply just the numbers. Okay, so you can multiply 25 by 25 by 9. All right, let's do that. So 25 times 25 times 9. So this is going to give you 5,000. It's going to give you 5,625 times. So once you have these lot of 10 to the power, it's simple to solve that. That's very simple. Okay. So 10 to the minus 7 times 10 to the minus. So you're going to add them. So this will be minus 14. You had minus 14 to plus 9, and that's going to give you minus 6, sorry, minus 5, sorry, plus, yeah, minus 5, right? Minus 5, yes. So just simple adding the suffix. So this would be 14 minus 14, and then so it's minus 5. So minus 5 right there. Okay, so all right. And again, so we can simplify this even more, Let's do that. So this is 5,625. So when you do that, this is actually 5.625. So it is 5.625. You have to multiply it now by 10 to the power 3 to get it to the same thing. So 10 to the power 3, positive 3. And then we had our 10 to the minus 5 right there. And then, of course, you have to divide by your d squared. D squared. D squared. Okay? So when we simplify this a little bit more, so this is 10 to the power 3, 10 to the minus 5. So this is 10 to the minus 2. So it is 5.625 times 10 to the minus 2. Still have your d squared below. So this is the electrical force, which is equal to our force due to gravity. So if you want to just stick it right here, it's equal to the force due to gravity, which is 1 times 10 to the, all right, just call it 9.8. So that's 9.8 times 10 to the minus 3. So the electrical force is equal to the force due to gravity. So we want the distance that balloon B must be above balloon A for it to levitate. So if we just rearrange this equation to get d squared, so d squared, so you always pay attention to your So d squared is equal to, so we're just rearranging this equation. So d squared is equal to 5.625 times 10 to the minus 2 divided by 9.8 divided by 9.8 times 9.8 times 10 to the minus 3 minus 3. Okay, so simplify that. So 5.625 divided by 9.8. Let's do that. Let's do that math. Okay, so 5.625 divided by 9.8. That is equal to 0.57. So that's equal to 0.574. So that's equal to 0.574 times. So we're dividing by 10 to the minus 3. So we have to, when we take it on top, it becomes positive. So it becomes 10 to the 3. So we're going to have 10 to the 3. So it becomes positive 10 to the 3. And we have a 10 to the minus 2 there. So when you simplify that, so you're going to have 0.574 times 10. But this is d squared. So this is equal to 5.74 so to get d, so d is the square root of that. So d is equal to the square root of 5.74. So the square root of 5.74 is, let's, so that comes out to, okay, let's see. All right. So that's going to be 2 point whatever. So you should get a calculator that can give you the square root of these different numbers. So again, so you get the square root of 5.74, and that will give that your answer is going to be in meters. Okay, it's going to be in meters. But the concept is get your electrical force, and they always bring questions about levitation. So how far up above you're gonna hold the object, or how far below you're gonna hold the object. Always remember that your electrical force is gonna be in, in a direction. If you have attraction, then the electrical force is going to be an attractive one. If it's repulsion, the electrical force is going to be a repulsive one. Your force due to gravity is always downwards. Okay? So you have to remember your electric force formula. Electric force formula states that the attraction between two charged objects is equal to K, which is the equation, the Coulomb law equation constant, times the charge on one object times the charge on the other object, divided by the separation distance. Okay, so that's the concept. The next thing we're going to discuss is electric field strength, but want you to get the concept of electric force, and then we will go on to electric field strength. So you're going to get a question in some fashion on electric force. The important thing is to know the formula and know how to use it. Again, remember you have to have the units. The units are important. Okay? SI units, the distance is in meter, charge is in coulomb, okay, force is in newtons. You have to have the units correct.